same way, because here in this chapter we are dealing with charges, electrostat. So if we have something like capacitance, तो उसका मतलब क्या होगा, क्या होना चाहिए? जो चार्ज को स्टोर करने की कैपेसिटी हो, कंडक्टर की चार्ज स्टोरिंग कैपेसिटी इज द कैपेसिटेंस। ओके, तो हर कंडक्टर की एक चार्ज को स्टोर करने की कैपेसिटी होती है, उसको उसका कैपेसिटेंस बोलते हैं। ठीक है, कितना चार्ज वो होल्ड कर सकता है, कितना चार्ज वो स्टोर कर सकता है। सो कैपेसिटर इज अ डिवाइस and capacitance we measure. See, as we have resistor and resistance that we have discussed in class 10th, lower classes we have studied. Okay, so if we have a resistor, the function of resistor is to resist the electric current, and we can measure resistance of a resistor. So resistance means, if we get high resistance means उतना ही strongly वो current को resist करेगा. If we get low resistance, तो उतना weakly वो current को resist करेगा. In the same way we have capacitor. It is a device which is used for storing charges, and we can measure capacitance of a capacitor. So this is the capacitor, you can see. Electrical capacitance or capacity of a conductor. It is the ability of a conductor to store an electric charge, and the charge on the plates of the capacitor is directly proportional to the potential difference at the two ends of the capacitor. Charge is directly proportional to potential difference. And to remove the sign of proportionality, we always add a constant. Yes, and here that constant is C. So Q is equal to CV, where C is the capacitance of the condenser or capacitor. Okay, we call capacitor a condenser as well. See, how can we measure this C? We can measure C by dividing Q and V. So C is equal to Q upon V. Its unit is farad or 1 coulomb per volt. Capacitance is measured in farad, and because C is Q upon V, na? So Q is measured in coulomb and potential difference is measured in volts. So 1 farad is 1 coulomb per volt. And dimensional formula we can easily find out. Find out karo. C is equal to Q upon V. Okay, and this charge can be written as IT. And what is this V? This is work done per unit charge, or we can write work upon IT. है ना? Work done per unit charge. Na? V is W by Q. V is W by Q, and Q is equal to IT. So when you'll put these values, these expressions here, what will you get? I square T square by W. So to find the dimension of C, we need to write the dimension of I. It's A square. For time, it is T square. And for work, no, it is. So capacitance is always positive. Symbol of capacitors. See, this is how we draw capacitor through two parallel lines. So these two are the plates of capacitor. One plate is positively charged and the other plate is negatively charged. So this capacitance of this capacitor is fixed. Okay, it is a fixed capacitor. And this is variable capacitor. 1 farad. So capacitance of a capacitor is said to be 1 farad. See, because C is Q upon V. So if charge is 1 coulomb and potential difference is 1 volt, only then capacitance is 1 farad. Okay. So it is said to be 1 farad if its potential rises through 1 volt when a charge of 1 coulomb is given to it. So if we give a charge of 1 coulomb to a condenser and its potential rises to 1 volt, then we say that capacitance of that capacitor is 1 farad. So when we give charge, potential rises. ऐसा होता है जब हम किसी कैपेसिटर को चार्ज करते हैं तो उसका पोटेंशियल राइज हो जाता है। क्यों, कैसे? देखो, सपोज वी हैव अ चार्ज, ठीक है? So due to this charge, we can find potential at some point P. The potential at P will be, if this point is at distance R, we can write potential as KQ by R. What if we increase the charge? So if we increase the charge to 2Q, then at the same point, if we find the potential difference, if we find the potential difference, yes, then it is K 2Q by R. So it's 2KQ by R. So if we increase the charge, then potential difference also increases. Yes, so charge and potential, they are directly proportional. है ना? Therefore, we write Q is proportional to V. And we write Q as CV. Okay? कॉन्सेप्ट समझ आ गया कि हम Q प्रोपोर्शनल टू V क्यों करते हैं? क्योंकि जैसे जैसे आप चार्ज की वैल्यू को इंक्रीज करोगे, आपका पोटेंशियल भी इंक्रीज हो जाएगा, है ना? KQ by R होता है, तो सेम पॉइंट पे अगर निकालोगे तो यू विल गेट 2KQ by R. So they are directly proportional. And this is equal to CV. C is the capacitance of the condenser or the conductor, whatever we have. Okay. Now this C is Q by V. So if we increase the charge of 1 coulomb, if a charge of 1 coulomb is given to a capacitor और उसका potential rise हो जाए by 1 volt, तो जो capacitance है उसका वो 1 farad होता है. ठीक है? So 1 farad can be written as 1 coulomb upon 1 volt. So if we want to write the SI unit, CGS unit of charge, then how do we write? In 1 coulomb, we have 3 into 10 raised to the power 9 stat coulomb. Yes. And in 1 volts, we have 1 upon 300 stat volt. So please find the value. What will you get? 3 3s are 9 into 10 raised to the power 11 stat farad. 1 farad is 9 into 10 power 11 stat farad. Clear? आ रहा है? ठीक है? Capacitance of an isolated spherical conductor. So if we have a spherical conductor, if we give charge to a spherical conductor, then whole charge reside on its outer surface. ये तो पता है हमें, है ना? When we give charge to a conductor, no charge resides inside the conductor. Whole charge resides on its outer surface. Suppose we have given charge Q to this conductor. And this is a spherical conductor. Let R be the radius of this spherical conductor. So if I ask you to write the expression for electric field intensity and potential difference inside the conductor, then can you please tell me what is the electric field intensity inside the conductor? It's 0. Electric field intensity inside the conductor is 0 because we have no charge here. Okay, but inside the conductor, electric potential is KQ by R. See, it is a constant here. Yes, because E is minus dV by dr. So if we have this electric field intensity is 0, है ना? When we do differentiation, and differential of a constant is 0, right? This implies V is a constant. So electric potential is constant inside the conductor. And on the surface of the conductor, what is electric field? It is KQ by R square, and electric potential is KQ by R. This is on the surface. ये क्या था? Inside the conductor. Yes? So we can easily find capacitance of this capacitor. How do we find C? C is Q upon V. And what is V? It is KQ by R. So put the value here. So C is Q upon V, Q upon KQ by R. So we'll get R upon K. And what is K? K is 1 upon 4 pi epsilon naught. So 1 upon K is 4 pi epsilon naught. So you can see this capacitance of this spherical condenser depends upon the radius of the condenser. If we increase the R, if we increase the radius of the spherical condenser, then capacitance will also increase. And if we decrease the radius, then capacitance will decrease. So we can conclude from here that capacitance of a conductor depends upon the shape and size of the conductor. Yes, it depends upon the shape and size of the conductor. Capacitance of earth. So now, because we know that for a spherical conductor, capacitance is 4 pi epsilon naught R, right? So if we know the radius of earth, we can easily find capacitance of earth. So what is the radius of earth? It is 6,400 kilometer, right? So in meters, we can write this as 6.4 into 10 raised to the power 6 meters. Now put the value here. It's 6.4 into 10 raised to the power 6. And 1 upon 4 pi epsilon naught is 9 into 10 raised to the power 9. Because 1 upon 4 pi epsilon naught is 9 into 10 raised to the power 9 Newton meter square per coulomb square. So this implies 4 pi epsilon naught will be 1 upon 9 into 10 raised to the power 9 coulomb square per Newton per meter square. Yes. Now on solving this, you will get the capacitance of the earth as 0.711 into 10 raised to the power minus 3 farad. Or we can write this in microfarad, 711 microfarad. This is the capacitance of earth. So this value is considered very large in the family of capacitors. Okay, this value is quite large. This 7.1, though it is in microfarad, but this is considered very large. Okay, therefore, earth can store unlimited charge. Diameter of a spherical conductor is 1 meter. What is its capacity? So we have a spherical conductor and its diameter is given. Diameter is 1 meter. What is the capacity of this spherical conductor? So because diameter is 1 meter, we can easily find radius, right? Yes? Radius is 0.5. Because capacitance of a spherical conductor is 4 pi epsilon naught R. Put the value here, 0.5 upon 9 into 10 raised to the power 9. And your answer is, बताओ? 55.5 picofarad. The potential difference of 250 volt is applied across the plates of a capacitor of 10 picofarad. Calculate the charge on the plates of the capacitor. The potential difference is given. It is 250 volts. Capacitance is 10 picofarad. Convert this in farad first. 1 picofarad is 10 to the power minus 12 farad. Okay. So it is 10 into 10 raised to the power minus 12 farad. 10 to the power minus 11 farad. We have to find charge. So charge is equal to, बताओ, Q is equal to? Q is equal to Q is equal to CV. Q is equal to CV. Now put the value. C is 10 to the power minus 11. and into 250 coulomb. Okay. So we can write this as 2.5 into 10 raised to the power minus 9 coulomb. See, in parallel plate capacitor, we have two plates which are parallel to each other. We have two conducting plates and they are separated by a small distance. Okay. So the distance between the plates is kept small like this. So you can see one plate is positively charged while the other plate is negatively charged, and we can see the lines of force here from positive charge to negative charge. So we can draw lines of force like this for a parallel plate capacitor. Now, what is the principle of parallel plate capacitor? On what principle does it work? To increase the capacity of one conducting plate A by bringing another conducting plate B close to it, to decrease the potential at the same charge. Explanation, it follows three cases. Step 1, देखो इसमें क्या है, we have this plate A. So this plate A is positively charged and this plate B is grounded. It is not grounded, but there is some kind of connection, you know, it is disconnected, you can see. It is disconnected. We can connect this to the ground at any time as and when required. So we have a positively charged plate. So these are two conducting plates. Okay. So A has positive charge and B has initially no charge. It is uncharged. It is uncharged. It does not mean that it doesn't carry charge. See, even uncharged conductors have charges in them, but they have equal number of positive and negative charges and therefore they are uncharged. But we can polarize the charges. है ना? अगर कोई कंडक्टर अनचार्ज्ड है उसका मतलब ये नहीं है कि उसमें चार्जेस है ही नहीं, उसमें चार्जेस हैं, बट उसमें पॉजिटिव और नेगेटिव चार्जेस का जो नंबर है वो इक्वल है. Okay, now if we bring this plate B very close to A, but we are not touching these plates, then what will happen? When uncharged plate B is closer to plate A, then due to induction, negative charge is induced on one face of the plate on the left side because this plate carries charge. It is a conductor. It's obvious that it has charges in it. So charges will polarize. So if we keep this plate B very close to A, then charges in plate B get polarized. So we will have negative charge on this side and positive on that side. Why negative on this side? Because all these negative charges, they are attracted to the positive plate and they move towards this side. On the other hand, positive charges in the plate B, they get repelled, they get repelled and move to the opposite side. So in this way, within the conductor, charges are separated, or polarized is the word for this. Charges are polarized within the conductor. The induced negative charge on plate B tends to decrease the potential of A, whereas induced positive charge on plate B tends to increase the potential of plate A. So this negative charge, you can see, it will decrease the potential and this positive charge will increase the potential of A. So what is the overall impact, overall effect? Will it remain the same or there will be any change? Same रहेगा. What do you say? Change होना चाहिए. How will it change? देखो, this is closer ना, this negative plate is closer to this positive plate. On the other hand, this positive plate is at a distance. So this is reducing the potential while positive is increasing the potential. So overall there will be decrease in potential because it is closer, so it is more effective. Are you getting what I'm saying? Yes. Because this plate is closer, so it is more effective. It is decreasing. It decreases and Therefore, net potential of plate A is decreased because this plate B is closer. Now, this side of plate B, negative side, is closer, so it has more impact on it. So overall potential of A will be reduced. Now, because potential of A is reduced, now we can give more charge to A. Okay. Now we can give more charge to A. Now what we'll do is we'll ground this side, positive side of the plate B. So when we ground this positive side of the plate B, so ground acts as source of electron as well as sink for electron. So in this particular situation, what do you think? It is acting as a source or sink of electron? This we had discussed in methods of charging, or I think earthing and grounding, that when we had done in the first chapter. Hmm? See, because we have positive charge here. So positive charges get neutralized only when they get negative charge. So they get negative charge from the ground. Only flow of electrons take place, no positive charges move. Okay. So ground acts as either source of electron or sink for electron. So in this particular situation, ground will act as source of electron. This ground will provide electrons to the positive side, and positive charges get neutralized due to those electrons, because of those electrons. Okay. So now we have only negative side of the plate. This positive side is grounded, na? So we have only negative side of the plate. So overall potential of A is greatly reduced because of this. Now because potential of plate A is further decreased. So we can give more charge to it, because now we can give more charge to it. So its capacity is increased. जितना ज्यादा वो चार्ज को कैरी कर सकता है, मतलब उसकी कैपेसिटी चार्ज को कैरी करने की इंक्रीज हो रही है, तो उसकी चार्ज कैरिंग कैपेसिटी इंक्रीज होने का मतलब ये है कि उसका कैपेसिटेंस इंक्रीज हो रहा है। ठीक है। डायमेंशनल फॉर्मूला ऑफ कैपेसिटेंस बताओ। यस, इट्स बी। सिंबल ऑफ वेरिएबल कैपेसिटर। गुड। Now we have a next topic, capacitance of parallel plate capacitor. Please write the heading. Draw a parallel plate capacitor like this. This plus sigma. Sigma we had done in charge distribution when we had covered charge distribution in the chapter 1, then we had done this. So plus sigma is the surface charge density of this plate, and this minus sigma is the surface charge density of second plate. Okay. So plate separation is D. Plate separation is D. So D is the distance between the two plates of the capacitor. We are assuming that plate A has positive charge plus Q, while plate B has negative charge minus Q. Plus sigma is the surface charge density of plate A, and minus sigma is the surface charge density of plate B. We have, if we have these three reasons, reason 1, reason 2, and reason 3. Okay. So this is positive charge and this is negative charge. So let E1 be the electric field intensity due to this plus Q, and E2 be the electric field intensity due to this minus Q charge. Okay. So what is the direction of electric field intensity due to plus Q? Away from the charge. E1 is acting, it will act in this direction. And what is the direction of E2? Towards negative charge. Similarly, if we find in reason 3, what is the direction of E1? Away from positive charge, and direction of E2 is towards negative charge. Okay. So because we know that E, electric field intensity, is sigma upon 2 epsilon naught. So this electric field intensity does not depend upon the distance. है ना? When we draw a graph E versus R, then we get this line parallel to R. So E is independent of R. Yes? Independent of distance. So it only depends upon the surface charge density. Yes? So in reason 1 and reason 3, net electric field intensity is 0. While in reason 2 we have, see, we have this positive charge. So this is the direction of E1. And for negative charge, E2 will act in the same direction which E1 is acting. So for reason 2, we can find net electric field as E1 plus E2 by adding these two. We will get the net electric field. So it is sigma upon 2 epsilon naught for first plate and sigma upon 2 epsilon naught for second plate, and the result is 2 sigma upon 2 epsilon naught. So it is sigma upon epsilon naught. And what is sigma? Sigma is the surface charge density, and it is equal to charge upon area. See, A is the area of each plate. Okay, A is the area of each plate. Clear? So we can write E as Q upon A epsilon naught. Also, we know that, E is minus dV by dr. It is potential gradient. Na? E is minus dV by dr. So we can write E as V upon d. So what is V? We can write V as Ed because E is V upon d. So V is Ed. Now put the value of expression for E here. It is Q upon A epsilon naught d. Done? Done? Okay. Now C is Q upon V. C is Q upon V. Put the expression of V here in this formula. What will you get? Q upon QD divided by A epsilon naught. On solving this, you will get epsilon naught A by D, where A is area of each plate and D is distance between the plates. Okay, so this is the expression for capacitance of a parallel plate capacitor. C is equal to epsilon naught A by D. Okay, so C is epsilon naught A by D. Now for A equals 1 millimeter square. If the area of each plate is not millimeter. If area of each plate is 1 meter square and distance between the plates is 1 millimeter. So can you find capacitance of the parallel plate capacitor? How will you find it? Find the capacitance. It is C. What is the value of epsilon naught? Yes. 8.85 times for minus 12. Area is 1 and distance between the plates is 1 millimeter is 10 for minus 3. 8. So capacitance will be 8.85 into 10 raised to the power minus 9 farad. And for if C is 1 farad and D is 1 millimeter, then we can find area. How will you find area? If C and D are given, we can easily find area using the same relation. So A is CD upon epsilon naught. Now put the values. C is 1, D is again 10 for minus 3 meter. Epsilon naught is 8.85 into 10 power minus 12. So your answer is 0.11 into 10 raised to the power 9 meter square, which is nearly equal to 10 raised to the power 9 meter square. See how big is 1 farad? We are getting this much area, na? 10 raised to the power 9 meter square is a big value. This is what I was trying to show you, that if you take area as 1 meter square and we are keeping the distance same. See, in both the cases, we have kept the distance same. Distance between the plates is 1 millimeter only. But here we have taken area as 1 meter square and we're getting this capacitance, which is quite small. But if we take capacitance as 1 farad, if we take area as 1 meter square, then we're getting this capacitance, which is quite small value, yes. But if we take capacitance as 1 farad then we are getting a big value of it. Yes, then area is 10 to the power 9. So this 1 farad value is quite large for a capacitor. Okay. So we can conclude that how big this 1 farad is. See, let this be the positive plate of the capacitor. And this is the negative plate. Of the capacitor. Let A be the area of each plate and D is the distance between the plates. And this system is in vacuum or in air. Then we can write the expression for capacitance as C is equal to epsilon naught A by T. Now we have this question that what if we, place this capacitor in a medium which is not air. Okay. What if we have a dielectric medium between the plates of the capacitor and this dielectric medium of dielectric constant K, let's say. Then, because of this dielectric, how will the capacitance of the capacitor change? This is the question. Okay, so because now, initially we had considered the case when we have nothing in between the plates. Now we are assuming that there is some substance, there is a dielectric medium. These plates are filled with the dielectric medium. Then what? So capacitance in the medium. Now capacitance will change. It becomes epsilon A by D. Epsilon naught will change to epsilon. This is the permittivity of air or vacuum. And this is the permittivity of a given medium. Okay. Now we know the relation, dielectric constant or relative permittivity is epsilon by epsilon naught. This is how we write. So we can write epsilon as K epsilon naught. Yes. So it is K epsilon naught A by D, and this epsilon naught A by D is C naught. So Cm is equal to Kc. Capacitance becomes K times when a dielectric medium is introduced between the plates. Okay. And K is Cm by C naught. So when an insulating material is introduced in the space between the charges, between the charged plates of the capacitor, its capacitance increases. Capacitance increases. Okay. If we introduce an insulating material in the space between the charged plates of the capacitor, then its capacitance increases. It becomes K times. From this, we can conclude that capacitance of a capacitor depends upon the nature of the medium. Capacitance depends upon the nature of the medium and also it depends upon the position of the neighboring charges. Position of the neighboring charges. Earlier we had done capacitance depends upon the shape and size of the conductor. Yes. So on these three factors, this value of C depends upon. Shape and size of the conductor. Capacitance depends upon the shape and size of the conductor, nature of the medium, and position of the neighboring charges. The capacity of a capacitor becomes 10 microfarad when the capacity of a capacitor becomes 10 microfarad when air between the plates is replaced by a dielectric constant of K equals 2. What is the capacity of the condenser with air in between the plates? So capacitance becomes 10 microfarad when a dielectric slab is introduced. So So this is the capacitance with dielectric slab. Yes, it becomes 10 microfarad, right? It becomes 10 microfarad when dielectric slab is introduced between the plates and dielectric constant is given, it is 2. Yes, so K is 2. We have to find the capacity of the condenser with air in between the plates. What if there is air? So how are they related? We know, no? This C is epsilon naught A by D. This is C naught. Okay. When we have air in between the plates, we write C naught. This is what we have to find out. And when we have a medium, then we write K C naught. This is how they are related. So we can find C naught as Cm by K. So 10 microfarad by 2. Answer is 5 microfarad. So we can easily see when there is air, then capacitance is 10 microfarad. But when we introduce a dielectric slab, then its capacitance increases to 10 microfarad. Double हो गई capacitance. सिर्फ एक dielectric slab introduce करने से capacitance 5 microfarad से 10 microfarad हो गई, double हो गई. So capacitance increases with K, with the introduction of K or with the introduction of a dielectric slab. Or when a capacitor is placed in a medium, its capacitance increases. Some equivalent resistance. Equivalent resistance is the effective resistance. अगर हमारे पास 3 resistors हैं and all those 3 resistors are connected in series, so we can replace those 3 by just one resistor, which will oppose the current with the same effort as is opposed by all the 3 resistors together. Right? That's equivalent resistance. In the same way, we can combine capacitors and we can also find equivalent capacitance. So equivalent capacitance is what is equivalent capacitance? Suppose we have 2-3 capacitors and we have connected those capacitors either in series or in parallel, then we can find equivalent capacitance. It means that in place of those 3 capacitors can be replaced by one capacitor, which will produce the same effect as produced by 3 capacitors together. And that's called equivalent capacitance. That's how we find equivalent capacitance. Okay. So combination of capacitors, either we connect capacitors in series or we can connect capacitors in parallel in the same way as we connect resistors. Okay. So if we have capacitors in series, so in series we know now potential difference, it changes. When we connect resistors in series, we had done that in series combination, current remains the same, but potential drop across each resistor changes. In the same way, we have, charge is same everywhere, but potential drop across each capacitor is different. So net potential is V. V1 is the potential drop across C1. V2 is the potential drop across C2. And V3 is the potential drop across C3. Okay. So initially, the plates of the capacitors are uncharged. There is no charge initially on the capacitors. Okay. But when we see this plus this plate of the capacitor C1, this red plate, it is connected to the positive terminal of the battery. Due to the electric field, this positive charge pulls negative charge up to the right plate C1 and till the electric field lines begin from the left plate and end on the right plate. Therefore, the right plate of C1 acquires negative charge, negative Q charge. Okay. And this negative Q, this negative charge comes from the left plate of C2 through the wire connected to them. Because this negative charge comes from the left plate of C2 through this wire connected to them, therefore this C2, this red plate acquires positive charge. Similarly, second plate will acquire negative charge. In the same way, all the plates get charged. Okay. So let V be the potential difference across the arrangement and it is divided as V1, V2 and V3. Let C1, C2, C3 be the capacitance. Okay. Because this is how we find net potential. No? V is V1 plus V2 plus V3. We'll simply add all the potential drop and we'll just equate it to net potential. So we'll get this. And this V is Q upon C. What is C? C is the equivalent capacitance. C is the equivalent capacitance. So, and for this arrangement, for this first C1 capacitor, we can write V1 as Q by C1. Similarly, we can write for second capacitor. बताओ क्या लिखेंगे? V2 as Q by C2. And for the third capacitor, it is Q3 by C3. Now we will put all these values here in the first equation. What is C? What is C? It is equivalent capacitance, and equivalent capacitance is the effective capacitance. Okay. Substitute all these terms in the first equation. So we'll get this. Now we can take Q outside, Q common, and we can cancel these Q's. So we'll get this. 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So when capacitors are connected in series, then we can simply add their reciprocals to get the net capacitance or equivalent capacitance. And if there are n capacitors in series, then if there are n capacitors in series, if the number of capacitors are 3, then we have added 3, 1 upon C1 plus 1 upon C2 plus 1 upon C3. If there are 4, then we'll add one more, 1 plus 1 plus 1 upon C4. If there are 5 capacitors, then we'll add plus 1 upon C5. Similarly, if we have n number of capacitors, then 1 by Cn. Okay. So we'll put this summation sign. I is equal to 1 to n. First, we'll put the value of I as 1 to 1 upon C1, then plus, because we have summation sign, we'll increase the value of I to 2. C2, then C3, then C4, C5 to Cn. Okay. If two capacitors are in series, then we write like this. For two capacitors, we can write like this. Okay. We can take the LCM. LCM of these two is C1, C2. In the numerator, we get C1 plus C2. Now take the reciprocal. To get this equivalent capacitance, we'll take the reciprocal. So C is C1, C2 upon C1 plus C2. This is for two capacitors. Similarly, if we have capacitors in parallel, then what? See, in parallel combination, potential drop across each, circuit, it remains the same. And potential drop, this V, it remains the same across each capacitor. In parallel circuit, we have V equal even for resistors. We have done this, right? We keep the V same and value of I changes. Through each branch, there is different current, and the value of current depends upon the resistance value. In the same way, here also, V is same for all capacitors, but we have different capacitors value. First capacitor has capacitance C1, second capacitor has capacitance C2, third capacitor has capacitance C3. Because they have different capacitance value, so different amount of charge can be stored. Na? If capacitance ज़्यादा होगा, तो more charge can be stored. है ना? Capacitance की value कम होगी, तो कम charge store कर सकते हैं. Since each capacitor has the same potential difference across it, so it is in a position to store charge according to its capacity. This is what I have said. ये अपनी capacity के according वो charge को store कर सकते हैं. Potential drop तो same है सबका. जिसकी जितनी capacity होगी, वो उतना charge store कर सकता है. ठीक है? Hence, capacitors have different amount of charges. Because they have different capacity, so they will store different amount of charges. So for C1, we are taking Q1, for C2, we are taking Q2, and for C3, we are taking Q3. And what is the net charge? Total charges? Q1 plus Q2 plus Q3. Okay, so Q is Q1 plus Q2 plus Q3. And this Q is the net charge. For net charge, we will write equivalent capacitance And net potential, yes, CV. So Q is equal to CV. And Q1 is for this combination. V is same for every, each and every combination we have the same value of V. So Q1 is C1V and Q2 is C2V, Q3 is C3V. Now put these values in the above equation. What will you get? For Q will write CV, for Q1, C1V, Q2, C2V, Q3, C3V. By putting all these values here, we'll get this relation as this. C is equal to C1 plus C2 plus C3. So in parallel combination, we simply add the capacitance. Resistance में उल्टा होता था. Resistance में series में हम ऐसे ऐड करते थे और parallel में हम reciprocals लेके ऐड करते थे. और capacitors में हम क्या करते हैं? Series में reciprocals लेके ऐड करते हैं और parallel में series simply ऐड करते हैं. ठीक है? If we have n capacitors connected in parallel, then yes, तो Cn तक हो जाएगा. So we can write like this. Summation I is equal to 1 to n Ci. Formula for effective capacitance of different capacitors when connected in parallel combination. बताओ. Parallel combination, it is not resistor, it is capacitor. A. Formula for effective capacitance of different capacitors when connected in series combination. Up से होगा. Right.